Interference. We all know how annoying it can be in the home, but in commerce, industry, and medicine, it can have far more serious implications, especially since we have come to rely more and more on electronic systems for communications, storage and processing of data, business and office automation, and for the automation and control of manufacturing, industrial, and other processes. The increasing importance of robotics, computer-integrated manufacturing, automated diagnostics, digital circuitry, and continuing miniaturization makes it ever more crucial to adequately protect against the disturbances caused by interference. And we can do this while working towards a higher degree of electromagnetic compatibility, which makes very good business sense.
The most common forms of interference are the radio frequency interference we've just seen and electrostatic discharge. There are two pathways between the source of disturbances and an apparatus, via electromagnetic fields or by conduction. These can cause intra-system compatibility problems, so appropriate measures have to be taken in the design stage to overcome such problems, and, in so doing, avoid the kind of budget overflow that's caused when you must redesign and redevelop to prevent disturbance. In addition, when you're forced to redesign, you end up with a much longer throughput time. So, prevention is much better than cure. Let's take a look at a topical demonstration of the damage that interference can cause. With the kind of thermostatically controlled ovens used in IC production, we find a thermocouple, a display, a computer to program the temperature profile and time setting for the oven, and of course the oven itself. In the absence of interference, the system will function as programmed. But it may be susceptible to the kind of high-frequency fields generated by a portaphone or an industrial high-frequency heating system. In the event of interference disturbing the computer, the system may still seem to be working perfectly as far as the operator can make out, but the actual temperature profile is no longer equivalent to that programmed. Minor and even major deviations are possible, depending on the frequency and intensity of the electromagnetic disturbance. This will result in an entire batch of ICs or wafers being produced wrongly to non-reproducible specifications. This non-reproducibility is totally unacceptable, and the, by now, costly batch of silicon material will have to be scrapped. This non-reproducibility is equally unacceptable in other fields, like medical diagnostics, where interference could lead to faulty diagnosis, with the risk of very serious repercussions. Or in continuous process industries like petrochemicals. And the higher the degree of automation, the more costly such interference can turn out to be. Just think what it would cost to scrap a day's production of an automated assembly line, or think of the havoc that an electromagnetically disturbed robot could wreak. There are many more well-documented case histories, or horror stories, about what interference can do, but we should have made our case by now. Namely, that it is absolutely essential that the importance of electromagnetic compatibility within our products and means of production is not only recognized, but accepted as a clearly defined activity that is fully integrated in the design process for all our products and means of production. However, electromagnetic compatibility is too big a problem for any one company to handle entirely on its own.
Certain countries already have regulations governing EMC at a national level. Internationally, there are IEC, CISPR working groups, but their valuable work results in recommendations which are not legally enforceable. However, the European community have now set objectives for electromagnetic compatibility, and products that fail to comply with national EMC regulations may find national borders becoming barriers. In the meanwhile, within the Philips concern, an EMC working group has been set up to harmonize the many existing standards into company-wide standards.
These are published in 2 parts, within a whole series about environmental requirements for equipment for professional use. They cover the frequency range from DC to several gigahertz. The standards make it easy to define EMC requirements for products before product development actually starts. The documents containing the standards have to be frequently updated to match the rapidly changing requirements and to retain their validity throughout commercial product definition. In this way, they can provide proper EMC guidelines that are applicable whether you decide to make or buy. But although this documentation helps, it still doesn't solve all our problems. For that, we need training in EMC techniques and in the EMC measuring methods that can be used in development. We need continuing investments for training and equipment and general EMC awareness.
The inductance of the inner conductor, and L sub S that of the screen. RS represents the series resistance. Applying Kirchhoff's law to the lower circuit, the red circuit here, yields this equation, where this term, K times Ls, represents the coupling between these 2 inductances. Here we apply with a square wave generator a signal via this cable to the load, the 50 ohm load, at this end. With this current probe, we can measure the current through the screen, and that gives the upper trace on the oscilloscope.
No single expert or group can solve the problems of EMC compatibility. So, within Philips, specialized information and training modules are set up to meet the specific needs of different groups. General management, article management, product management, electrical and mechanical designers and engineers, purchasing officers, sales engineers, assembly line workers, and of course our customers are all directly involved. And as this graph shows, the earlier the integration, the lower the cost of EMC measures. So that before the product designer starts his work, an EMC strategy can be set by the product team to fully integrate the EMC requirements into our products from the very beginning of product development. This is based on product complexity, the size of production runs, and manufacturer capability studies. A complete EMC strategy can be worked out for the product. Furthermore, a time schedule for EMC verification must also be planned. Many of today's Philips products are built around a number of printed circuit boards. So when a designer has completed the particular prototype board for which he is responsible, he can test it for electromagnetic compatibility on his workbench before it is integrated into the final product. The board can be tested both for electromagnetic emission as well as susceptibility to emission. This kind of testing of individual boards by individual designers helps eliminate intra-system incompatibility and speeds up the total development. Final testing of products for electromagnetic compatibility is most commonly done on an open test site. But the high level of man-made noise, disturbance by transmitters and so on often makes this impossible. A good solution is to build a Faraday cage, like this one at the Philips Research Laboratories in Eindhoven. The material on the walls absorbs the electromagnetic energy. Since interference can neither enter nor escape from such a shielded enclosure, it is feasible to automate measurement to a great extent. Here, too, products sold under the Philips label but made by third parties are evaluated before market release so that any problems can be anticipated.
All this effort is directed at making electromagnetic compatibility an integral part of our products, for very practical reasons, namely to speed up development and reduce integral costs. Because the costs are not only determined by the product itself, but also by the effort that service or customer support have to put into projects to get systems running satisfactorily. And this is something that can and must save Philips and its customers a lot in the future. Proper electromagnetic compatibility by our products means satisfied customers and greater quality. Much valuable work has already been done within Philips. Conductive plastics, metal lacquers, and copper-clad aluminum printed circuit boards and special coax cables have been developed to provide economical means for achieving compatibility. We all have to become EMC-minded, but there's still a lot to be done. Just compare those early CDs with today's models, which contain the same functions but do not need all the additional shielding measures. The bottom line, as our graph has shown, is that the earlier you integrate EMC measures into your product, the less they cost. And finally, in an era in which digital electronic circuitry is working at ever higher speeds, at higher packing densities, with computer-integrated manufacturing and local area networking penetrating factories and offices to an even higher degree, electromagnetic compatibility is more essential than ever before. And in the end, proper EMC is a question of good workmanship and plain good business sense.